excuse me. So hello, good morning, everybody. Thank you very much for being here again for the Laboratoire colloquium at the IAA. It's an absolute honor for us to have here Professor José Pelló. Pelló. She's the principal investigator of an instrument for the extremely large telescope, which is, I guess you agree, our future. So José Pelló is a senior astronomer at the Laboratoire d'Astrophysique de Marseille in France. Her research focuses on galaxy formation and evolution, gravitational lensing, cosmological surveys, and instrumental developments. After completing her PhD at the University of Barcelona, she obtained a permanent position as assistant astronomer at the Observatoire Midi-Pyrénées in Toulouse, in France, in 1992. Since then, she has been heavily involved in several scientific and instrumental projects, such as MUSE for the VLT and Euclid. In 2019, she moved to her current position at the Laboratoire d'Astrophysique de Marseille, where she's the responsible for the MOSAIC instrument for the ELT, as I said. It's an absolute honor, as I said, for us to have her here, and with for an instrument for which we have a commitment as a center and as a Laboratoire center. Thank you very much, José, for being here. Thank you to you for the introduction. So let me put the chronometer because I tend to speak too long. So I'm going to present today the instrument MOSAIC in different respects. The first thing I want to say is that thank you. Well, I want to say thank you to the organizers for allowing me to present this instrument to you today. It takes most of my time, so I'm very proud to present this. And the second thing I want to say is that this is the work of a team that I'm going to present. So we are a team, a science team, but also an engineer team, very strong one, with people from very different countries, different laboratories, etc. So forgive me if I present this myself, but of course I am presenting this, keep in mind, on behalf of the MOSAIC consortium, and many people in the audience are part of it already. So thank you for your work. Now, it's very well. Something is not working really. No, it's not moving on. Oh, sorry. Okay, so I like this image because I think it's very important to keep in mind that we are working for the ELT, and the ELT is becoming a reality. So it's no longer an artist's view or something. It's really looking like this. This image was taken in July this year. And you can see that the telescope is taking shape, and the improvement and the evolution of the construction is really now spectacular. More than 70% of the total work has been done, and the telescope is now looking like as if it was finished, right? But there are still many work to do. Now, let me present briefly what I'm going to talk about today. I'm going to introduce very briefly the status of the ELT and MOSAIC in it. And then I spend most of my time on two different topics. First, I will introduce the MOSAIC as an instrument. I will give you an overview, as well as the project status very briefly. And then I will take most of my time to speak about the MOSAIC science cases and science working groups that we have currently in this consortium. And of course, I hope to have some time at the end for a discussion with you. But I'm going to stay here, as it was said before, tomorrow as well, so you can take the opportunity to discuss with me if we don't have time today. Now, a little bit of a history here. Essentially, the ELT has been a long date project. The first study started 20 years ago, in 2005, if I'm not mistaken, with the selection of the site. 5 years after that, it was Cerro Almazones in the Atacama Desert, only 23 kilometers away. You can see this on the right-hand side, only 23 kilometers away from the site of the VLT that you all know. It's a
more than 3,000 meters height observatory. And the construction was actually approved in 2012, and the building permit arrived in 2014. However, things were progressing very, very slowly, and the work on the dome started only in 2018. You can see here how it looked like at that time and how it looks like today. Today, 70% of the structure has been completed. The first light will arrive early 2029, and we expect the first astronomical observations in 2030. Keep these values in mind, it's not so far away from now. What is the ELT? Well, you all know possibly it's this monster here, about 100 meters height as compared to things that you know, in particular the VLTs. It's a primary mirror with almost 800 segments that are aligned all together to better than 10 nanometers. This is really something impressive. And the cost is about 1.5 billion euros. This is also important to know. And of course, this is without accounting for the instrumentation, which is also part of it. Many people have been working on this telescope construction since a long time. This is just to remember you that the ELT is a monster, the first in its class. It's one of these bigger telescopes, gigantic telescopes as the TMT and the GMT. Unfortunately, TMT and GMT are not progressing very well at the moment. I'm not going to comment on this. You can immediately realize the importance of the ELT when you compare the size of the mirrors. Here you have in green the size of the ELT that we are talking about as compared to the famous TMT and the GMT. And what is possibly more impressive is when you compare the size of this telescope, it's 39-meter diameter, with the size of a basketball court or with a tennis court. Actually, the Nasmyth platforms are as big as a tennis court. Well, possibly you remember this very nice image. It was only 2 years ago. This is the image of the ELT as it was 2 years ago, as seen from the VLT, so 23 kilometers away. And this image also corresponded to this. This was in October, or almost 2 years ago, as I said. So you can see the work was really in progress, not very well advanced. Please compare this to how it looks like today in July 2025. I could have chosen another picture, but this one is very nice. So you can see the spectacular improvement and the speed of this work. This is to show that the cladding was at that time almost completed. And the main structure of the telescope, you can see here the main characteristics. It's more than 3,000 tons, okay, of optomechanics and electronics. You have a pointing accuracy of 0.3 arc seconds. If this is not impressive, I don't know what impressive means. And you can move from one pointing to another in typically 5 minutes. So this is something really incredible. We will have 2 Nasmyth platforms and a CUDA room for the instruments. A very quick reminder of what the ELT means in terms of the optics of the mirrors. The primary mirror is 39 meters, as I said before, but also you have 5 mirrors. So you have M2, M3. These one are respectively the biggest convex and the biggest concave mirrors ever built, about 4 meter diameter. The M4 is the largest deformable adaptive mirror ever built as well, more than 5,000 actuators on it. And this M4 works together with M5, which is a tip tilt mirror to stabilize the images. And essentially this system fits the instruments located in the Nasmyth platform, in particular MOSAIC. So MOSAIC will be located in one of the 2 Nasmyth platforms. This is still an artist's view. The size of this platform is quite impressive, 50 meters each one. And of course, the light is given by this prefocal station, PFS, that distributes the light platform. This PFS is also quite impressive. You can see here the image as it is built at IDOM in Spain. And as far as I understand, it has been already delivered. It takes always a few months between the delivery and the approval. So I think it's approved. And this is very important. You can see here some people, just to compare the size of the thing. So MOSAIC will be immediately behind the top of this structure. So this is how it's going to look like. So MOSAIC will be over there, as I said. And possibly it's important for you to remind what the current calendar is in terms of the availability of the ELT. You have here an updated calendar provided by one of the ISO colleagues, and you can see the delivery of the different mirrors here with the dates, the typical dates. So we are here at the end of 2025, and you see that essentially everything will be completed here at the beginning of 2029. This is why I mentioned that this is the first expected light, and then about, let's say, 1 year after that, we will have the first scientific light. This is, of course, quite a certain period, how long it's going to take, because as you know, it's a new telescope, so we are going to discover many things. Well, and then after this, the different instruments will arrive. I want to mention something that is very important for us, MOSAIC. These are the different instruments, 1, 2, 3, 4. Look at this thing. There are no names here, because instruments will arrive progressively as soon as they are ready, right? When one instrument reaches a readiness level that allows it to go to the telescope, it will go to the telescope. Possibly the first two will be Mikado and Metis. This is almost sure. Also Morpheus, but then, well, the others, as soon as they are ready. MOSAIC is part of it. Okay? Well, so this was what I wanted to say as an introduction for the ELT. Let's move on now to MOSAIC itself. MOSAIC. So what is MOSAIC? If I have to present MOSAIC, I will say, well, it's very easy. I need only one sentence. MOSAIC is the multi-object spectrograph for the ELT. So the rest, you know, we will locate it in one of the Nasmith platforms. However, don't forget that MOSAIC is the result of many years of work by many people and different, let's say, former designs that were built to fulfill the needs of the multi-object spectroscopy at the ELT. And it is not a simple thing. I will cite here the old Eagle project, for instance, Optimus Eve or Optimus Dioramas, all of them led by people. Possibly some of you in the audience were already part of it at that time. I remember myself being part of Eagle at the time, but it was really a very old story. And you have to create all these people, because without these people, we will never be there. Okay, now more about MOSAIC. What MOSAIC is going to do? You see here an artist view, and on the right-hand side here, on the bottom left side, you have the most recent, let's say, design of the instrument, as it was presented in the Progress meeting, I think. So MOSAIC is going to have very precise characteristics that make it unique. It will cover a very wide wavelength domain, from as blue as the ELT can provide to 1.8 microns in the near infrared. All the electromagnetic spectrum will be covered. Also very important, MOSAIC is going to use the maximum field of view that the ELT can provide, that is about 40 square arc minutes on the focal plane. This is quite unique because all the instruments of the arriving first and the other instruments only use the central part of the ELT. MOSAIC is going to use a large portion of the focal plane. And we will have two observing modes, a classical mode and a multi-IFU. All these modes are fiber feed, so meaning that MOSAIC is a fiber instrument. And there is a reason for this. I'm going to show you this in a minute. First, when you look at this, you see the main pieces of MOSAIC. I'm not going to enter into many details, but essentially the light enters here from the prefocal station, arrives to the focal plane, and we have a device that I'm going to describe in a minute to capture the light. And this big structure here containing this focal plane, fiber positioners, optical relays, etc., etc. All this is in the top, on top of the structure, okay, with this mechanical support. All this is what we call the front end. And then we have two other big pieces, big channels. We call these channels. One is the visible spectrograph here on the platform, or if you want here, the visible spectrograph that I'm going to describe. And then the third one, and possibly for people working in the distant universe, the most important one, is the near-infrared channel here with two twin spectrographs, also in the platform. Just to give you an idea of the dimension of this is about 11.5 by 8, and the height is, I think, to the top. Remember, it was 12 meters for the prefocal station, so it's the same for here. This means that if I take my home and I put it inside this volume, I still have some room for a garden around. Okay, just to give you an idea. You cannot see it like this, but yeah, you understand what I mean. So now what I'm going to do is to describe very, very quickly the different challenging aspects of this instrument. The first one is the focal plane itself, because the ELT is non-telecentric. So if we want to use the full focal plane, we need to correct for this non-telecentricity locally. And this is what we do with MOSAIC. You can see the situation here on this design on the left hand side, where you see that essentially it's all but flat, okay? So we have to follow this shape by using a design that provides a tile and a stepped focal plane. Then, in this focal plane, if you look at it from above, you will see something looking like this on the right-hand side, and you see the extent of the field. The diameter that is going to be useful for science is about 7.5 arcminutes diameter. You see here the imprints of the laser wave field sensors. It's either natural guide stars or laser guide stars. So this is the adaptive optic system of MOSAIC. And all these cells you can see here carry this. There are 300 tiles, and all of them carry one peak of mirror and also one single or double fiber feet. So at the end, we have 500 fiber feet. And the different colors correspond to different combinations of these fiber feet in such a way that you can combine different observing modes, okay, in one single shot, in one single exposure. This will be very interesting for parallel observations. What you have here in the center, I'm going to show it in the next slide, are the different apertures for the multi-object mode, where you have the fiber bundles capturing the light of each one of the targets. We don't use single fibers, we use fiber bundles. And you have here the structure of these fiber bundles to the right scale for the visible mode, the near-infrared mode, high and low resolution, and the multi-object facility, which provides these apertures. There are 8 apertures like this, with a size of 2.2 arc seconds, which is the right size to capture the kinematics of very distant galaxies at redshift 2 to typically to 4. Well, this is in more details how it looks like. And this is how the current design presented at the last progress meeting looks like of this focal plane, as you can see here, with the mechanical actuators, all these different cells carrying these fiber positioners in each one of them. Essentially, it has been demonstrated that you can essentially cover all the objects across the field, that more than 80% of the objects that you have as initial targets by using this system, allowing you to move these robots in these small cells everywhere. So it's a very efficient system. This is a little bit to show how it works. It's not at the scale, but it gives you a good idea. This is the tiled focal plane that I mentioned before. Oh, sorry. Okay. This is the tiled focal plane here. And essentially, you have two different types of observing modes here. The light arrives from the left, and it reaches each one of these fiber positioners, these small robots, and it's sent either to one or the other of the fiber bundles. Okay. Sorry. Sorry. Oh, no. Sorry. I'm sorry.
This port is really messed up.
That's okay.
Okay.
Ah, I just moved the cable.
So now you're
Sorry.
It's
Sorry,
not-
sorry. I was not trying to break the material.
Just don't move the rest.
Sorry, sorry.
It's all good.
So here you have the different situation. So as I said, you can either send the light to the through the most optical path, meaning that you send to one of these fiber bundles that are taking the light, sending it to the spectrograph in the Nasmith platform, or you can through these mirrors send them to the optical relays. There are 8 of them. And in this case, you feed the mini IFU, and you have 8 IFUs that you can locate everywhere on this field of view. Well, I have to say that this design is very useful for engineers, not necessarily for me to explain this to you, but this is to give you an idea about the complexity. And this is possibly the most challenging part of the instrument because of the size of this. It has never been done before. But fiber spectrographs fit like this already exist. Look at MOON, for instance, or PFS. So we are just following the path of existing spectrographs, so the risk is less. But I have to recognize that it is quite complex. This is how this focal plane looks like. This is a very recent design. This was for reference. This was given at the SAR. So we have the 3 different possibilities of parallel observations you can combine. You have in the near infrared, you will have 185 tiles. In the visible low resolution, 145. And in the high resolution, it's less because of the space in the design, in the collecting surface of the cameras. Only 68 of the tiles will fit this high resolution mode. Okay, so this is how it looks like. Possibly I can comment on that, but I will just repeat what I said before. So now let me a little bit describe the 2 different spectrographs and the capabilities, and then I will summarize all this for the astronomers here. If I focus on the visible channel, this design on the right is a little bit old, but just to remember, this is this thing. This channel has been optimized for galactic studies, essentially, to provide high survey speed and stability, essentially. So the visible spectrograph has 2 different arms, a red arm and a blue arm. You have here the sketch of the optical design. And you can feed these 2 different spectrograph, these 2 different arms with, let's say, to observe in the low and the high resolutions. Okay, different modes. The different resolution modes are given in this table. Roughly speaking, you have the wavelength here, and you have the resolving power as a function of wavelengths. So the red and the blue arms see complete in one single shot in low resolution, around 5,000, in one shot all the electromagnetic spectrum in the low resolution mode. Okay, so there's no choice here. You can take everything in a single shot, and then the 4 high resolution modes focus on windows that are very interesting for stellar studies in the local universe. And you can combine, for instance, one of these 2 in the blue high resolution modes with the low resolution in the red, and the opposite, etc. So essentially, in one single shot, you can have one of those and this complete, or one of the red and this. So you can combine all this. You know, the high resolution mode reaches, well, as you can see here, this is a resolving power going from typically 18,000 to 20,000. This is how it looks like, seen from different ways. So we have the red and the blue. The advantage of doing this, here you have the size as well, 4.3 meters and 3 meters side. So this is relatively big and also 3 meters high. Okay. So the interest of doing that is that you can optimize the detectors in such a way that you optimize the red and the blue separately. So this is a nice story. We'll go into it in many details. Now, if you look at the near infrared channel, in this case, it was optimized differently it's also optimized for faint sources and optical sky subtraction. This is the main problem in the near infrared due to the skylines. And in this case, the design is very close following or derived from the moon concept as well, but of course it has been changed a lot to actually correspond to the current design. This is a design including two different cameras, a G camera and an H camera, covering completely the wavelength domain from 0.95 microns to 1.8, okay, in one single shot again. And you can also have a high resolution window in the H1. So high resolution is around, as in the visible, around between 18,000 and 30,000, and the low resolution mode is around 5,000 in resolving power. In one shot, you have all the electromagnetic spectrum in the near infrared, or you can combine the low resolution in J and the high resolution in H. And here, the only mobile piece will be the grating here. And we have only one camera in H and one camera in J. Well, here is how this design looks like in the 3 dimensions, seeing from above, seeing from the side. Some colleagues here in the audience could explain this much better than myself, so I'm going to stay to the basic things. So something I want to mention is that the two spectrographs are twin. They are not symmetrical or whatever, twin, because it's easier to build and less risky and expensive. And of course, here I had a very nice movie that cannot work because I'm using the PDF, because my PowerPoint was not working. There's no problem. So here you have a little bit how it's going to look like when the engineers will be proceeding with the commissioning, etc. Nanophonics. Of course, there is a history of these stairs. It was there, and now it's here, and it's, the site design has changed many times. I'm not going to enter into these details. This is just for fun. If you are an astronomer, the only thing you are interested in is this, possibly a summary of all these different modes. So as an astronomer, you will go to the tables and see, well, what I can do with MOSAIC. This is what you can do. You have two different modes, the MOS mode and the multi-IFU mode. In the MOS mode, you can choose between the visible and the near infrared. You combine the two as well, as I mentioned before, with different multiplex capabilities that are given here. And if you observe with the multi-IFU mode, we are going to observe in the near infrared only. You have 8 of these devices of this size, and you cover essentially in the low resolution all the window between 0.95 and 1.8 millimeters. Okay, and here I have a no-fault table, just because of questions. Because if then some of you ask, yes, but what are precisely the wavelengths covered by this or that high resolution mode, high resolution window? This table summarizes all this. Okay, so you have for the low resolution and the high resolution the different wavelength domains that are covered in one single shot, and the resolving powers here as well, and a very last color here that is very important because it provides the limiting magnitude in all these different observing modes. What I call here limiting magnitudes is arbitrarily set to a signal to noise 5 for 5 hours exposure over periods. Okay, so remember that you can observe simultaneously in several cases, and there are many combinations that we can use for your observations. And also remember that you can cover in one single shot, in low resolution mode, completely the visible domain plus the near infrared domain, but of course not for the same object. Okay? Meaning that you can combine all this together. Okay, this graph is also awful. As a function of the wavelength, you have these limiting magnitudes in the center of the different bands. Well, I should not move. Okay. I'm trying to stay stable. Okay. So you have as a function of the wavelength, you have these limiting magnitudes that correspond to the average in the different bands. And you can see how the low resolution mode, this is the orange line, will be very efficient for surveys. This is in the continuum, of course. Okay, you can observe much fainter objects where you are only focusing on one single or given emission line or emission lines. Okay, same thing. This is the continuum. And the same thing in the high resolution mode here, where you are most focusing on the third populations in the local universe. But you need a high signal to noise, and you can go up to, as you can see here, quite easily to 24 or so, no problem, 25 even, because this project. It is important to say that MOSAIC is a quite unique instrument, as I said. And what is the situation today? I have tried to update these graphs I'm going to show. However, they are still the official ones of ESO, so I'm going to keep them. This is to locate MOSAIC in the landscape of ELT instrumentation. Well, MOSAIC will be only spectroscopic, have only spectroscopic mode, and it is quite unique why I'm saying this, because as compared to the other instruments given in different colors, MOSAIC is essentially occupying this big region here in the middle. It's going blue. It's providing the bluest wavelengths that the ELT can provide, and up to 1.8, as I said. And of course, with binning, etc., you can essentially cover this region in the resolving power domain. And also, in terms of the field of view, this is a log scale where the field of view is compared to the spatial resolution. And you see MOSAIC there, over there, in the right hand side corner, in the top, meaning that MOSAIC is really providing the largest possible field of view. So essentially, in these two graphs, you see immediately that MOSAIC will be quite unique, providing multiplex capability, moderate spectral resolution in the vis and the near infrared, and the only one providing this large field of view. If somebody asks you, please retain that. So it's optimized, as I said before, to provide the highest survey speed. This has been the driver, and also a high sensitivity for observing sources with very low surface brightness. And so, just one word, this will be, I hope so, your favorite follow-up machine for all these space missions and ground-based experiments that today have already started or will be starting in the next coming years. I put a list here, but I'm going to mention this much further later. Well, why this is completely biased? I agree. Why this large field of view is important? Well, I'm just giving you two examples. This is the field of view of MOSAIC as compared to the field of view where this protocluster candidate at redshift 9-ish have been discovered, thanks to James Webb this year. I'm not sure that the paper is already accepted, but okay. So look, if you want to confirm all of them, you take this field of view, you take MOSAIC, a few exposures will be enough to confirm or infirm this kind of findings. And I can tell you MOSAIC will be the only one able to do so. And also, I couldn't resist to compare the field of view of MOSAIC to the field of view of one of these lensing clusters, where you can see in this area, you cover at the same time the very high magnification domain that has been covered by other instruments like MUSE, for example, and also regions where the magnification is moderate, but still providing an efficient extra push to observe, why not, the first stars or even first protoclusters behind, as some people have started to suggest. So also here in this case, the field of view is the one that you really need. Well, now I'm done with this. A few slides to show you the project status and where we are. So MOSAIC is a big consortium. As I put here in this table, 25 institutional partners, 33 laboratories, 14 countries, and more than 350 members. And why it's so big? Because the consortium is responsible for raising complete construction funding and for all commissioning and construction, etc. So we will be rewarded by ESO by doing all the work and in addition to find all the funding that we need to complete the instrument. I provide here some milestones that we have in mind. This is our internal milestones, right? The goal milestones. We are now somewhere here. We have started the B2 phase with the kickoff meeting, and now we are moving towards the ESO PDR. Okay. And we expect, for the moment, nothing prevents from doing that. Huh? I mean, this is clear. And we could, in the best possible case, be in Almazones with accepted in Almazones in 34. This is the faster we can go. Okay, let's be honest. Realistically. However, of course, if you look at the contract, here is some of the contract dates, they have an extra time because in the contract we of course secure that we can do it in the time. This is going to, as you can see here, extend everything up to 36 and even to 34, 38. Sorry, if you consider also the 2 years that are needed between the acceptance and then the final acceptance, what is called the final acceptance, in case you discover something is wrong or something. So this is the contractual part, but of course we want to do it as fast as possible, and it's very important to do so. And also it's important to know that we can shorten some of the dates that are imposed by ISO just by reducing the time needed, for instance, by doing in parallel some things, and this is perfectly doable. Where we are, well, we have here the major milestones of the project until now. You have to know that MOSAIC was approved by the Council at the end 2021, and it was approved on the basis of a gateway at the founding review. Then we had the kickoff meeting for the B1 phase in March 2023. We signed later because there is always a time between the official kickoff and the practical kickoff and the official kickoff due to the delays in the signatures. In June 2024, we had the SRR, the System Requirement Review. In end of April 2020 this year, we passed the SAR. This was very important because this was the end of the phase B1. We received the notification saying, well, SAR is passed beginning of July, and we started in mid-September the phase B2 with the kickoff meeting in the Jalan. You see the picture there with some people. Most people attended remotely to this. Also very important, we had a consortium science meeting end of October in Amsterdam. Some of you were there attending this meeting. It was very important because it was the kickoff meeting for the Red Book that will be a major publication that is part of the deliverables of the PDR. And this was last week, on Monday, we signed until the construction with ISO, and now we are essentially, now we have the stamp, and we can go to the construction until the end with this famous founding review that will follow the PDR, where we have to agree and to sign with our blood, and this will never be moved again. The guaranteed time we receive for MOSAIC. Okay? I think that this is just one comment is that, as I said, remember these famous channels, the front end, the V's, and the near channel. Here in Granada, you are working in the near infrared channel, the near infrared channel that is under the Spanish responsibility. In any case, this is where the channel will be integrated to start with. And so this is the structure of the project at the moment. And we have introduced some changes since the SAR, in particular by including new people in the project office, but this is an organizational thing. So I'm going to stop here with this and now move on very quickly towards the science. So I'm going to take your questions after that, if you agree. Yes? So I move on. Okay. As I said before, well, MOSAIC will cover a large domain of scientific topics. From the perspective of MOSAIC, we have 6, well, in fact, it's 5, because 2 of the science working groups have emerged. We have 5 very powerful science working groups that have coordinators and a large number of members, sometimes belonging to different science working groups. Why it's important to get organized like this? Because all the nights we will receive as a GTO will be dedicated to and shared as MOSAIC surveys, instead of providing a few nights to everyone. So we all take benefit from this. We'll have more papers, more results, more exchanges, etc., etc. If you look at the science team, we are now more than 250 people belonging to 14 countries. And there is a large representation in Spain, but it could be improved. Okay? Be prepared for this Red Book, because it will be prepared and published together with the PDR. And this, we hope, will be a very important publication of MOSAIC, a very well cited, we hope as well. Well, the science working groups are as follows. We have the first light galaxies and reionization, inventory of matter. Then we have mass assembly of galaxies through cosmic ages. This is a very wide science working group. We have a very important science working group around stellar populations in and beyond the Milky Way with different aspects that are very important because MOSAIC will be quite unique here. And then we have a new a time domain, transients, and multi-messenger that will be with less members, that will be more taking advantage from opportunities, but it's also important. Now let me summarize a little bit some of the different topics that can be addressed with MOSAIC and that cannot be addressed with other facilities, very often in close synergy with other facilities. Remember that we don't have imaging mode in MOSAIC, right? Well, of course, this is completely biased, and some of these topics are not at all my topic, the topics I know. So please forgive me in advance. I apologize in advance because it's not going to be complete. So possibly you can complete them with your comments. Okay, so this is the first one, is about the stellar populations in and beyond the Milky Way. In this case, we want to explore the star formation and chemical enrichment histories beyond the let's say the local group, if possible. And essentially, what we want to do is to overcome the limitations of the current 8 to 10 meter telescopes, thanks to a high sensitivity. We have a more collecting power, we have more sensitivity, and a high multiplex. So, in particular, we can prove further down color magnitude diagrams going, for instance, to the domain of the dwarf stars, whereas now we are limited to giant stars. Diagnostics will be based on several features, and don't be surprised that these features, if you are in the domain, will be precisely located in these windows where we have high resolution modes. So we will have two different things here. Either we use the very high resolution of MOSAIC to resolve intrinsic species for brighter objects, or we use the lower resolution and we take benefit from the high signal to noise. So the two will be possible, and the colleagues have plenty of ideas to take benefit from this. For instance, this is something that was already explained long ago during the first version of the instrument, is that we will have, for instance, with MOSAIC, spectroscopy for mid to late O-type dwarfs, up to 3 megaparsecs, or to reach farther away giants and supergiants, doing a step further with respect to everything we are doing today. So essentially proving massive stars in a wide range of galaxies, for instance, so to see the role of environment, something that we cannot do today. Well, this is just an example taken from a recent publication, essentially showing typically the magnitudes in these color magnitude diagrams that we will want to reach to really make progress. And with MOSAICs, if you remember my tables before, we will go between 24 and 25 here, so you can see that this will be very nice. Well, people working on galaxy archaeology will be also very happy because we can analyze the metallicity distribution functions of the stellar population in the local universe, and targeting in particular, stars in the halo and the bulge, but also dwarf spheroidals and ultra diffuse dwarfs in the local group. And I provide here again one example. This is for the Draco 2. It's not my domain, so forgive me if I say things completely crazy. But just to look at the field of view that we will want to cover, again, look at this. This is a field of view of typically 10 arc-minutes. In the center of this, you can essentially cover the important fraction of the stars at the same time with MOSAIC. And here again, the high resolution observations are limited with 10 meter telescopes, and MOSAIC will permit to go much further. One like to remember what is important here for this new time domain, transients and multi-messenger, because it covers different aspects of these different astrophysical objects. And there is a lot of work now trying to investigate how MOSAIC can be the most efficient in solving some of the current questions and hot topics that will appear in particular in the future, together with the LISA, for instance, experiment starting in the 35. So MOSAIC will be very well suited for this. Of course, this is not driving the science, or the science is not driving the design of MOSAIC. This is why it is a little bit apart. but it is it will be very efficient, in particular, to survey the fields where these tangents take place, and to nicely complement other facilities that will be available at that time. A few words about this topic. I'm starting from high Z to lower Z. Of course, now we are in the era of James Webb Space Telescope, so we cannot ignore that. Okay, if you look at the places where the first stars are being formed until the full realization of the universe, we are talking about this redshift here between, possibly 20 or 30 years that, galaxies are being discovered by James Webb up to 14 or 15. And then reionization ends at 5.5 something, the latest ideas. And we have plenty of different ways of selecting these galaxies, depending on what kind of pre-selection you made, so to study them. And essentially, what is important for MOSAIC will be the capability of collecting photons of MOSAIC plus ELT is 40 times larger than James Webb. However, the price to pay is that observations will be carried out between the skylines. But, okay, we can live with this. In particular, there are challenges and open questions that have been raised by James Webb during the very first years of operation, like, for instance, the excess of bright galaxies and star formation at very high redshift, about 8, or the fact that you have quenched galaxies at redshift about 7, or you have AGN signatures at very high redshift, but with very low signal to noise. So, okay, what MOSAIC will provide is high resolution enough to see very well with high signal to noise these lines that are really important to characterize the sources, not just to say, hey, look, the redshift is this. Oh, I discovered a new redshift, high redshift galaxy. No, there is a high redshift galaxy there, and then you look to characterize this galaxy and to extract the physical properties. This is what MOSAIC will do that James Webb cannot do today. So MOSAIC can play a major role in addressing these questions. There is plenty of information in the UV res frame of galaxies of this kind that MOSAIC will be targeting in the near infrared. So this is why we are going to use preferentially the high multiplex in the near infrared and the multi-IFE, okay, as well. Just to give you a couple of examples, here they are these galaxies already discovered in 2023, I think, by James Webb. For instance, these galaxies that are very red, you see here the best fit, set fit, etc. And sometimes, well, if you detect Lyman alpha, you're happy. If you can have observation further with bright emission lines, okay. But if your galaxy is a passive kind of post-starburst galaxy, you will be in trouble. So this is where MOSAIC will be very good. And this window where these galaxies are being found between 7 and 10, let's say, or so, this is precisely the window where we will capture the near UV, and we can start doing. What you have here on the right-hand side is just, it was done long ago, but it's still true, is that we can reach enough signal to noise, let's say, for in the continuum with a reasonable exposure time of 10 hours, let's say, for objects like this, that have a continuum here in these windows, where, the majority of these bright galaxies want to study with. Same thing for this, okay, you can still capture bright galaxies at a redshift of 13, let's say, 13-ish. And this is an example, for instance, here for this galaxy reported quite recently. I can provide many examples. I'm not going to still with more. I just summarize this. There are many aspects that can be addressed with MOSAIC in this specific topic. For instance, the spectroscopy of the first stars with a little bit of push of gravitational lensing. So the properties of the first protoclusters in the early universe, the formation and evolution of the first AGNs, because this we will be able to capture these characteristics, and of course the metal content of the primeval galaxies, which is of prima importance. And of course, we are clear synergies with James Webb, ALMA, SKA, other ELT instruments like Mikado or Harmony to better capture the center with higher spectral resolution of these galaxies. Okay, what about the inventory of matter? This is the side working group 2. Okay, I have covered many of them already. Fourth here. So it is about the answering to these big questions that still remain in the literature, like what is the baryon budget in the CGM over time, how do galaxies accrete their gas and a function of the environment, all about dark matter and dark matter versus baryonic matter, the distribution, profiles, etc. This will be possible to follow until redshift much higher compared to what is possible to do today with 10-meter telescope. And of course, the interplay between galaxies and intergalactic medium. All these questions can be addressed by MOSAIC. For instance, just to provide you an example, this is extracted from one publication, a previous publication of Gensler, for instance, this very nice rotation curves. Today, we have with VLT studies of the inner dark matter content up to redshift of 1 to typically 2-ish. With MOSAIC, in the multi-IFU mode, we will be able to measure the same things, same profiles of galaxies, but much beyond this, extending the studies up to redshift of 4. I'm very sorry, but just, I mean, it is like before the breakfast, okay, in the cosmic history. And to measure this, we need really MOSAIC. So we will be able to conduct the first studies on the evolution of the dark matter content, and as a function of mass and redshift, and things like the evolution of the stellar versus kilomass, the transformation efficiency, and the evolution of the disk and halo angular momentum. This will be perfectly in the scope of MOSAIC. This is a very nice project. I want to mention is that we will be able to map the cold gas distribution of the cosmic web, okay, through redshift and scales that are not accessible today. Today we perform this exercise with quasars, for instance, so you have some limited lines of sight, but with MOSAIC we can use normal galaxies, star-forming galaxies, to do the same exercise. And this is shown by this simulation, where you can see that we can retrieve the original structure of the cosmic web by using MOSAIC and galaxies that are located at redshift above 3, typically observed with the BIS spectrograph, and then you see all the absorbance, and these can be used to reconstitute, to recover the 3-dimensional structure. So this is very nice. And of course, I can mention many other science cases of this kind, for instance, about mass assembly of galaxies. You have several key projects that were presented. I'm not going to repeat, slides are available. These were also introduced during the consortium meeting end of October. And essentially what you can see is that MOSAIC will be able to reconstruct the resolved properties of galaxies, disk and spheroid formation, kinematics of stars, many things like protocluster formation, stellar population, star formation, history, of course, and even precision cosmology and other topics that are very interesting and can be addressed by MOSAIC. This is an old simulation showing how a galaxy of different stellar mass can be reconstructed at redshift around 4, based on, for instance, here you have the reference case at redshift 0, different aspects like the kinematics, like the velocity dispersion, etc., or the maps of a specific element like oxygen 2, for instance. These are the 3 maps, and then you can see how they will look like. They look like at redshift 4, okay, for different galaxies, scaled, you know, as a function of the M star in the mass function. So you see that possibly you can see this just by eye. Possibly it will be very difficult here, but essentially for the bright galaxies, we will be able to play the game at redshift 4 very, very well. I want to mention the fact, and this is going to be one of my last slides, don't be worried. I just want to mention that MOSAIC will be this leading follow-up machine I mentioned before, in synergy with many instruments, with many other projects. I list here some of them with corresponding features. We have some specific examples that I'm not going to read for all these each one of the science cases, like for galaxies during the epoch of the reionization between James Webb, SK, and MOSAIC. The study of dense stellar regions by using MOSAIC, moons and harmony, for instance, galaxy assembly by using different combinations of this. I mean, there are plenty of cases where we use in a combined way MOSAIC with other facilities. And this, we have to keep this for sure, and of course follow up with gravitational waves, the environment of gravitational waves. So I have to try to keep in the 15 minutes. So this is a summary of the messages to take home. If you are an astronomer, please remember that MOSAIC will be possibly your favorite follow-up instrument for detailed studies of the astrophysical objects that you really are favorite astrophysical objects, in particular in the extragalactic, but also in the stellar domain. I just summarize here the main characteristics that you know, because I've already explained this many times. Just to keep something in mind, if you are people deciding about the use or not of the founding, keep in mind that MOSAIC is a complex instrument, it's true, but it is designed following proven concepts, meaning that the risk is low. So it's relatively low risk. And so how you can imagine that a telescope like the ELT do not have a multi-object spectrograph, right? So, okay, I'm just letting you with this. I already did this, so, and I take all your questions. Apologies for being too long. Yeah.
Thanks for this complete and interesting talk, Rosette. We have time for questions.
So, yeah, just very technical. So the parallel observing modes, can you elaborate a bit more? I didn't understand. So you can observe simultaneously in different different modes, IFU, mini IFUs, and MOS.
It depends on what you can observe with the mini IFUs in the near infrared, while you are observing in the MOS mode in the visible.
Okay.
The same field.
And you can combine spectral resolutions as well.
Absolutely, as I said before. For instance, you have 4 in the visible. You have 4 different windows for the high resolution, 2 in the blue, 2 in the red. And then you have the 2 low resolution windows in the blue and the red. You can take one of the 2 high resolution windows in the blue with the low resolution in the red and the opposite. And this can be observed simultaneously.
Thanks so much, Rosette. I'm sure you're aware of people being interested already in using MOSAIC for many other scientific research projects. Since we are here at the IAA, quite a broad scientific interest, could you tell us some of the other things that people are proposing to do and not including already in the GTO time for the projects?
I think this question can be answered in 2 different ways. The first is that whereas we are trying to, some of the science cases that have been proposed in these 5 science working groups have been used to dimension the instrument and to push the design, right? I'm not talking here about the transients, but for the others, yes. So this is why the visible spectrum is optimized in a given way, and the infrared is optimized in another way. So we have been trying to take into account the main types of observation, the observation type that we would like to conduct with them. And the Red Book will collect some of the reference projects that have been proposed by the different science groups. However, the room will be kept for new projects that we are appearing with time. This, for instance, I want to mention here the experience of MUSE. In MUSE, we had a lot of GTO as well. Several projects were very well defined, like here, but things changed, scientifically speaking, between the beginning of the operations and then by 10 years of GTO. It's a long time. So you need to allocate changes in the priorities according to what the community, So even from the GTO point of view, we already foresee to do so, to really keep open to new propositions by the community. So it's not at all close to this. This is what I wanted to say. Okay, and so this means that you have an idea, you can write a paper proposing this idea, and then this will be discussed. There will be a survey and publication board that will keep track of this. And yes, it's a very good idea. Let's go for it and implement the next time we implement. Let's implement this. This is how it's going to go. So yes, there will be a committee of people precisely taking care of this kind of modifications to be introduced, new projects, new ideas. So we will want to be as open as possible.
I mean, I was just wondering whether the people interested in exoplanets which are using those kind of spectral resolutions would be maybe thinking about using that kind of.
Well, possibly for exoplanets, these are individual objects, and other instruments will be much better suited than MOSAIC, because we are talking about the capability of multi-object capability. Yeah. However, for people working, you know, in with big objects of the solar system, like big planets, etc., they are interested. Look at different things at the same time, provided that you can have a guiding system that is not like a guiding system that allows to do so. And this is not in our hands; it's not us to decide. It's easy. But I took this idea, and they could be interested. So people working on some aspects of the planetary sciences could be as well interested. Of course, you have here in the ELT, you have I forgot to mention this in the given slide, but you are already involved, but you could be even more involved with other ideas and that enlarge this field. You need to be, and you will have the information, but you need to be a little bit waiting for the launch of the Red Book. I have not talked about this because this is the science working group coordinators to do so, but this is going to be done very soon. And the organization of this will take a long time because it will be launched typically at the beginning of 2026, and this needs to be completed by first quarter of 2027 or so, typically. So this will be an intense period, and I think it will be the time for the scientists to get close to these different groups and propose ideas, and just sometimes a small paragraph. It will be signed by a lot of people, this Red Book, and all the people who can be working on the different science groups is welcome.
Thank you, Rosa, for the nice talk and the very illustrative for all of us. I have just two questions. The first one is related to what you mentioned. These are the instruments. 1, 2, 3, 4, no names. So that means that phase B, phase this kind of thing, first and second round instruments is no longer.
Well, there is a change in the paradigm. At the beginning, people started when I started with the project was first generation, second generation. I suddenly discovered that second generation was never approved by the council. It does not exist. Okay, then I said, well, so should be renamed first light, first generation. So we are first generation. Started to give my talks by saying, well, we are first generation because this is what we are, right? We are not Mikado, Metis, or Morfeo, but we are, among the first generation, the only ones that are approved by the council, right? And then they have even changed this because it's much easier also for us collecting the funding for building these instruments. Is to say, well, let's talk about readiness state. Actually, when you reach an even readiness state, if you check the box, then you can consider applying for the commission in the telescope. So this is the thing.
So the ESO is prepared to.
Yes, they are preparing now that have typically 6 months between the moment where you start one instrument and one complete year, full year for commissioning an instrument, but you have 2 platforms, and you can rotate and accept a new instrument every 6 months.
Okay.
This is what they foresee now. Because I didn't exist in the timeline, but it's the plan. It's in the plan.
Okay.
Yes.
Good. And the other thing was maybe I missed something, but maybe you can elaborate. What is the relation with the adaptive optics or GLAO or?
Yeah, well, we have GLAO with natural stars and laser stars. But this is essentially the basic adaptive optics we have. We will not have more than that. This is not the proposal of MOSAIC, and we are already dealing with the focal plane that is not easy to deal with because it's we don't know precisely to the level we want to know exactly the geometry of this focal plane and how we can deal with this. So this is the objective of MOSAIC, is to be to maximize efficiency in the solvers. And other instruments using only the central part of the focal plane, they will have much better, as you can see in the second, my slides will show much quality with respect to field of view. MOSAIC is going to the, to the extreme in terms of the field of view, but of course it's sacrificing the adaptive optics and a high level of that.
Correct.
But there is no choice. I mean, this is what is available today.
Thank you.
More questions? I have a question. Maybe it's interesting for the audience to know a little bit more on how the guaranteed time will be spent, surveys. Can you comment?
Yeah, well, this is what I said. I mean, the guaranteed time will be entirely 100% dedicated to these shared surveys. I mean, there will not be individual allocation of GTO. When a partner accepts to be part of this, accepts also this commitment to use the GTO in this way. And this means that, well, because of this combined observations, we will need to choose to select very precisely the fields of view we want to observe for the different types of projects, to agree on the time to spend, but then nothing prevents, for instance, having longer exposure times in the visible, shorter in the near infrared, because this is controlled at the spectrograph level. You are feeding the spectrograph at the same time. So this is controlled in another level. So you can combine different observations from different science cases together. Of course, from the stellar part will be a little bit different. I mean, stellar part will follow one path, and then from the extragalactic, you can point anyway. So then the idea is to find the best possible places in the sky where observation already existing allows us to extract the maximum, right? But this will the GTO will be completely shared.
Yeah, but my point is that all the observations will go to a unique box, and everybody in the scientific team will have the possibility to look. And
Yeah. I mean, this is not yet decided, but it will be because we have time in front of us. But we did this. I have the experience of doing this in the Muse project, and I don't see why we could not do the same in MOSAIC. Of course, we are committed to deliver a certain number of tools to ESO that are mandatory, compulsory for everyone to use, for the data reduction, for instance. But then nothing prevents us preparing for the observation of MOSAIC to build those specific tools that we need for our science. And these are not deliverable. This is for us. And we share. So the idea is to share the maximum of these tools and to share the maximum of the data. So once you are inside, and then you will have an MOU to explain how we can share this data outside the collaboration, right? There's all the consortium. But the idea is to keep the data open and as much as possible, and also to share as much as possible the tools, dedicated tools that we are going to use, for instance, for sky subtraction, for the reconstruction of the velocity fields or whatever. I mean, different things. This is going to be shared as much as possible. This is a
More questions? So if not, just an announcement, we'll continue with a tapas session close to here. So whoever is interested is invited to join us in some minutes at the main entrance of the institute. Okay? And now thanks again.
Sì, nessuno, sono io.